Okay, here we go. I think we got it. I'm recording so that I can put it on YouTube so people can see it that aren't here, because we seem to be having.
You should become YouTube famous.
Yeah, seem to be having some various things coming up. So I did that the other day, and
The chemistry YouTube
so
videos
we'll do
aren't as good as
that.
the biology ones.
Yeah, the ballot. What?
The chemistry YouTube videos aren't as good as like biology YouTube videos.
Oh, I'm sorry. So Mondays is up there because there were some people gone and everything. So I don't know. We'll try it. Okay. So anyway, let's go over what we're doing, and then I need a few minutes to finish up the buffers, and then that's where we're going to stop. So here is the game plan. We're going to split this chapter. And we're going to stop at Henderson-Hasselbalch, which is slide 71 if you're playing along at home on the PowerPoint. We're going to stop at Henderson-Hasselbalch, and everything Henderson-Hasselbalch on, which would be equivalence points, titrations, and complex ions, we are going to do after break. Okay? So buffers will be on tomorrow's test. We're going to finish that up real quickly. But Henderson-Hasselbalch is where I'm drawing the line. So that means that all of chapter 14 is on it. And then section 1 from chapter 15 and section 2, but no Henderson-Hasselbalch, because Henderson-Hasselbalch is one way you can solve the stuff from section 2 in chapter 15, and then you can also do it with an ice table. So since we know how to do ice tables already, I'm just going to show you the ice table method, and then we'll do the other one after break. Okay? So section 15.2, except we're not doing the Henderson-Hasselbalch method. And then everything past that is going to be after spring break. So if we draw the line there, that means that 1 through 10 on WebAssign, okay, 11 through 15 are going to be after that, and I've already extended the dates, so that way they'll be up over break, and that week we come back, okay? So I've already extended the dates on it, but for tomorrow, you only have to have 1 through 10 done. Okay? The problems, you go up through 1532. Okay, so I think there's 5 problems in chapter 15, and then there's some in another chapter, like 21 or something. Those get chopped off. Okay, so you do all the chapter 14 ones. And then 15, you do the first 2, 31 and 32. And that's where the line gets drawn, so we're not going past that line. Anything that has something to do with Henderson-Hasselbalch, titrations, or complex ions is after break. Okay? Everybody with me there? Yeah.
So how many questions does that bring us down to?
Okay, so what I did was, I chopped down the test, and then I actually put some stuff back in, so it's actually a 90-point test. The free response is going to be only part of a free response because I had to chop out the buffer capacity and titration part to it. So you're only getting part of a free response. You're only getting part of the multiple choice. And then what I did was I kept the pH thing and then I put in the Bronsted-Lowry because I had cut it out because of time, and so I put it back in. So part 1 of the test will be find the pH of, and then you're going to have like 8 problems. Okay? Some of them will be strong acids, some of them will be strong bases, Some of them will be weak acids, some of them will be weak bases, and some of them will be salts, and some of them will be buffers. So you have to recognize which one it is and find the pH of it. Okay, so that's part one, and that's like half the points. Find the pH of this one, this one, this one, this one, this one, and this one, this one, and this one.
How many of those are there?
8. And there's, what, 6 types, so there'll be like 2 of a couple. But, you know, you can bet there will be 1 of each at least, and then a couple of them will have 2. So, strong acid, strong base, weak acid, weak base, salt, buffer. Okay, so find the pH of those. Section 2 will be reactions, and you label them with the Bronsted-Lowry labels. So, acid, base, conjugate acid, conjugate base. So I'm going to give you the equation. You just label which one's the acid, which one's the base, which one's the conjugate acid, which one's the conjugate base. And then part 3 is the abbreviated multiple choice, and part 4 is the abbreviated free response. So that's what's on the test. But as far as topics go, Henderson-Hasselbalch on will not be on it, because we didn't have time to get all that in. And I didn't want to cram today full of stuff, so we're just going to finish up the buffers, which is like 3 slides, I think, at most, and we'll call it. Okay? Everybody clear on what's on it, what's not on it, where we're stopping? Okay. So, and that's the website, so I've got it zoomed in. You can't really tell it, but that's the website. I put that up yesterday for some of you who caught that. If you happen to catch it on, or happen to think to look, or you saw Twitter or Facebook, I put a little note out about it. So, there it is. Okay? So, let me finish up. Pardon me. Let me finish up the buffer stuff, and then we can get to whatever we need to do. I backed up just a little bit here just to kind of catch us back up to where we were. We were looking at these 3, and we were trying to decide if they were buffers or not. And if you remember, a buffer has 2 requirements. One, it has to have a weak acid or base. And 2, it has to have a salt that has the same ion in it that the acid or base has. That's called a common ion. And the effect of that salt having that common ion shift the equilibrium is called the common ion effect. And so what happens in a buffer is that you add those ions, which will cause a shift in the equilibrium. And that shift in equilibrium will basically neutralize any acid or base that is added to that solution. So if I come along and dump some acid in, it will shift so that it will neutralize all of that, which means the pH is going to stay relatively constant. It might change, 0.01 or something, but it's going to basically keep the pH constant. That's the whole idea of a buffer. So which of these are buffers? What about A? A is definitely a buffer, okay? I have a weak acid HF. HF is a weak acid. And KF is a salt that has a common ion. F negative is a common ion to HF. So A is definitely a buffer. Oh, yeah, it is a typo, sorry. Yeah, HF is a weak acid, and F negative is its conjugate base. Sorry. Yep, you're right. Okay, so that is a buffer. How about B? B is not a buffer because HCl is a strong acid. So I have an acid and I have a salt containing a common ion. Problem is that this is strong, so there's not an equilibrium present. So this is not going to be able to shift because there's no equilibrium to shift. So B is not a buffer solution. Now, what about C? C is a little tricky. There's a common ion. Is there? Now this one's a little sneaky. HCO3 negative is the conjugate acid of carbonate. There is a hydrogen there, and so the bicarbonate ion can act as an acid. So while it is sodium hydrogen carbonate, there is a hydrogen there. So it's a little sneaky. It didn't start with H, but there is an H there, and it is an acidic hydrogen. So yes, that one is a buffer. That one was sneaky. But actually that one will work as a buffer. Because the bicarb ion does have that H, and it is, pardon me, ionizable. So a little sneaky, but yes, that would create a buffer. Okay, now
as hydronium ions are added
let's look at this video here about adding an acid to a buffer. Okay, so if I add HCl, that's a strong acid. That's going to give me hydronium ions or hydrogen ions, whichever, and chloride ions. If I dump this into a buffer, this is going to provide hydrogen ions. And that buffer is going to try to neutralize all of that to keep the pH constant.
The acid first ionizes in the aqueous solution. As hydronium ions are added to the buffer, the equilibrium shifts left, according to Le Chatelier's principle. Initially, in this acetic acid acetate buffer, there is a new acetic acid molecule formed for nearly every hydronium added to the solution. As the added hydronium ions react with acetate ions, equilibrium between acetic acid and acetate ions is reestablished. Only a very small amount of acetic acid ionizes to form acetate ions and new hydronium ions. The animation illustrates this process. Here, a hydrogen chloride molecule ionizes in water. The resulting hydronium ion reacts with an acetate ion, forming acetic acid. Due to the small Ka of acetic acid, very few acetic acid molecules ionize to form acetate and hydronium ions.
Okay, so this whole idea of this buffer is to have those common ions stockpiled. To have those common ions sitting there waiting for acid to come along. Those ions want to cause a shift to the left. Okay? Because remember, if we add something, that makes it shift away from it. Okay? So if I add those common ions, it's going to want to shift to the left. The problem is, it's a limiting reactant situation. If I don't have enough hydrogen ions for it to go left, then it can't go left until those acid ions, acidic hydrogens, come along. And when they do, those common ions are just sitting there waiting on them to show up, and pow, they get them and they shift to the left. So as soon as they go in, they combine with it and it shifts to the left, and that keeps the pH right where it was to start with. Now, this is going to show you what that would look like in a lab situation.
Resist changes to pH upon addition of
Okay,
small
so this
amounts
is a
of
buffer,
acid or base.
this isn't.
Each solution here starts at pH 9.25. The solution on the left is not a buffer solution. Click the button to add the strong acid HCl.
Okay, so I've got sodium hydroxide and hydrochloric acid, that's strong acid, strong base, and right now we're sitting at 9.25. Now I'm going to add some acid. This is a buffer, this isn't. This went all the way to 3.74. This went to 9.23. .22. Okay, I'm essentially keeping the pH the same as I add this. This one is dropping. Now eventually I can keep adding this and adding this and adding this, and eventually I'm going to run out of those common ions, and when I run out of those common ions, this one's going to start dropping like a rock. Okay, that's called exceeding the buffer capacity, and we'll talk more about that after break. But you can bust the buffer. It's not like you can add acid forever and that pH won't change. But until you run out of those common ions, it's a limiting reactant thing. Okay, when you run out of those common ions, then it can't buffer anymore. But as long as you have a source of those common ions, it's going to keep buffering. Okay, so let me show you the problem. Here is a solution. Is this a buffer, first of all? Is that a buffer? Yes. How do we know it's a buffer? I have a weak acid, and this salt contains a common ion. So yes, this is a buffer. That's a formate ion, I believe. It's an organic polyatomic ion. I think that's formate, if I remember right. I think that's formic acid. Okay, so this acid, this weak acid, change colors. since it's a weak acid, is going to form an equilibrium. And I'm going to get H plus, and I'm going to get HCOO negative. Okay, so this H, remember the H usually breaks off on the OH, so I took this H instead of that H. Not that it's going to make a whole lot of difference to you, but that's the H that comes off. Okay? That's an equilibrium. That's a weak acid. Okay? So this is going to have a Ka, right? Okay? Now, I've got this salt, HCOOK. Now, what's that salt going to do? What do salts do when you throw them in water? It dissolves. How much does it dissolve? 100%. So this is going to HCOO and K plus 100%. That is not an equilibrium. Now, here's the deal. There's a common ion here. If there were not a common ion, this would have no effect on this. But since this ion is the same as this ion, this is going to cause a shift in the equilibrium. And if I add that ion, what way is that equilibrium going to shift? Left, correct? If I add this ion, it's going to go left if there's an H plus to go with it. So what we're doing is we're stockpiling these ions so that they're sitting there waiting for an H plus to come along. And if an H plus comes along, if I dump in some acid after this thing has reached equilibrium, that acid is going to bond with one of these ions, and this thing is going left, which means the equilibrium ends up right back where it was. When I get rid of that H plus, that means that the pH is not going to change. That's what a buffer does. So the buffer is this part. It's this weak acid, but this one ion, this common ion, is affecting this equilibrium. So my equilibrium is still Ka. It's still H plus times HCOO negative over HCOOH. That does not change a bit. What changes is right here. Because I have two sources of this ion. I have the ones that form from ionizing, which is going to be X. And I have these from ionizing, which is going to be .52. If this is 100%, right? If this started out at 0.52 and 100% of this ionizes, this is 0.52, This is 0.52, and now this is 0. Right? No equilibrium there. That's just stoic. So when I set up my ice table, this is going to be what? .30. This is going to be 0. This is going to be 0 plus 0.52. Because remember, I have 2 places where I'm going to get those ions. I'm going to get ions from the acid, which starts out at 0, and I'm going to start out with 0.52 from the salt. So the only difference on these problems is right here. I have to add those 2 together because they are in common. From here on out, this is a plain old Ka problem. That's the only thing that's different. Is that I have 2 sources. I have these, and I have these. And I have to add those together. From here on out, it's just your plain old regular problem. This is minus x, this is plus x, this is plus x. So this is 0.3 minus x, x, and 0.52 plus x.
Again, Ka from the table.
And you get Ka from the table, and away you go. And since we're not finding any conjugates or anything, the Ka will be right in the table. You don't have to use Kw to switch it over or anything like that. Okay? The only difference is that yellow part. Otherwise, this is a Ka problem. This is a weak acid problem. The only difference is I have to add those common ions in. Is everybody with me on the ice table? Everybody see what I did here? Understand what I did and why I did it? So you look up this acid in your Ka table and you solve it. And boy, I hope this thing approximates. Because, yeah, this is going to get really messy. Not, you know, you can do it. It's just a pain. Because now I've got 0.52 plus x, so I got a binomial here, and then I got a binomial here. So that means I got to do more distributing and more collecting of terms and everything before I do the quadratic. But it can be done. Sure would be nice, though, if this would approximate. Unfortunately, this one doesn't. But I'll go ahead and show you what it would be. Usually, in fact, that Henderson-Hasselbalch that we're going to do after spring break, the one disadvantage to it is that you have to approximate, no matter what. This one is 10 to the minus 4, so that's right on the edge of being approximatable, if that's a word. Okay, so yeah, it gets you close, but it does throw it off a little bit. But it's close.
Guys,
Okay. Is everybody okay here with what we're doing? Now, here it is all nice and neat. This Ka is 1.8 times 10 to the negative 4. So you got to set all that up, and if you do all that ugly math and distribute all that out and get the quadratic and do x and everything, you get this. So you get a pH of 3.98. Now, if you went ahead and approximated this would be x times 0.52 over 0.3.
152 plus x.
No, not if you
Oh
approximate.
yeah, that's right.
So you don't even have to square root this one. So if you approximate, this is a cinch. Yeah, because this drops on the approximation and this drops on the approximation. And so all you got to do is plug that in, divide, you're done. And it'll get you close. This one's pushing the limit, but it'll get you close. Now, you know, in reality, I can't give you a whole bunch of these on a test because you're going to spend, 5 minutes just distributing all that mess out. So AP is usually pretty nice about giving you ones that you can approximate on. Okay. There might be one thrown in there occasionally, but that's about it. Okay, so watch for that, but a lot of the times you can approximate. I don't know how bad that one is if you approximate compared to what it's supposed to be, but I don't think it's very far off. Okay, so that's where we draw the line. This is where the stopping point is. The Henderson-Hasselbalch is another way to do this, and it's a little more convenient sometimes, so I'll show you how to do that. I'm not a big fan, but it definitely does make some problems a lot easier, so I'll go ahead and show it to you. But you've been doing this method all along, so to me this makes sense, because all I got to do is add those together, and then I just keep doing the same old thing that I've been doing. So the approximation worked? Oh, nice. Nice. Yeah. Well, good.
If we approximate and we're really close, will we still take out 1?
Yeah.
If we're off by 0.2, will you take out 1?
Yes.
0.1.
Yes.
0.09.
No. If you're out that last sig fig, nah. There you have it.
Just go over number 10.
There's your buffers, and that's your wrap. Number 10.
Yeah. Is that a salt one?
I don't know. Let's see. Yes, those are salts. So KNO2 would have come from KOH and HNO2. If we go back in time. So that's going to make this salt
Basic.
So I'm going to set up a KB. Now the KB needs to be for the conjugate base. So is this the conjugate base or is this the conjugate base? That one. So NO2 negative is the conjugate base. Yeah. This came from KOH and HNO2. This is a weak acid, this is a strong base, so that means this is going to be basic. So I have to set up KB for the conjugate base. So the conjugate base is either this one or this one. And since this one is a better proton acceptor, this must be the conjugate base. This would be the conjugate acid. So don't set that one up, because that one's going to be the wrong one. I know that this has to be a base because this is a strong base and this is a weak acid. So I know it has to be for a base. So there has to be a base that goes right here. And the only base that I have that's weak, you know, I don't want this one because this is strong, and I don't have that anymore. That's what it came from. Okay, so this stuff is not in the realm of possibility. This is water, so that's not in possibility. So these are the only possible things that I can work with. And this is a conjugate acid, this is a conjugate base. So this is my conjugate base. Okay, so my conjugate base is going to form an equilibrium, and bases make OH and HNO2. Okay, you may want to add the water here so that way you see where your H's and OH's are coming from, so it doesn't look like they're coming out of thin air. Okay, but if this is a base, that means it's a proton acceptor, so it's going to become HNO2. I add an H and I add a plus. So that gives me HNO2, and that leaves behind OH negative. So this is going to be OH negative, and this is going to be HNO2 up here. So that's the KB that I set up.
So you just set up an equilibrium for the NO2 plus H2O?
Yeah, so this is going to be point 1,5
0,
0 minus x plus x plus x. So 0.15 minus x, x, x. Plug them in. Now, you may or may not be able to find a KB for NO2 negative. My guess is you won't be able to find it. So, since you need the KB for NO2 negative, what you may have to do is look up the Ka for HNO2 and then do KW over Ka to get the KB. Oops, that's B. So you may have to derive the KB.
Ka for HN.
Yeah, because KW is Ka times KB. So what you may have to do is look up HNO2 and then flip it. So you may have to derive the KB to get it. I don't remember. There's usually one in the appendix. Yeah,
So
I'll try try the appendix.
Should we just Google some of this case?
I mean, they're all in there, it's just you gotta flip it.
And then you're giving us a table for the test.
Yeah, I'm giving you the tables out of the book for the test.
Like number 8 or something.
KSP, yeah, there it is, that's stepwise. And then there should be one, yeah, K, there you go. Okay, and then the same thing for B. B is going to be a base, and then C is going to be an acid. But that's 10.
So basically things with oxygens are going to be bases.
And not necessarily. No, you got to go back and look and see what they came from. All right, what else can I help you with? Anybody? Yep, that's fine. Okay, I will upload this to YouTube so you can review it if you need to. And for those of you who aren't here, hi.
I just like wait.
Yeah, I'll put
And
that up.
Michelle.
Yeah, hi Michelle.
Skipping school.
Hi Taylor.
Out.
Yeah.
The people who are left
So.
out.
I'll get this posted so you can look at it, and remember, if you forget where the line is, I've got it on the website, but the line is at Henderson-Hasselbach. We are not doing Henderson-Hasselbach yet.
Oh, I was like,
Okay, anything that says something about titration, equivalence point, or complex ion, that's after break.
So we're just having like a quiz after
Yeah.
like right after break?
No.
Monday?
No.
Like Thursday or Friday?
We're going to go over the material first. Then we'll have a quiz.
Well,
How
like,
many-
robotics is
Although
gone.
I guess just to change things up, we can do the quiz and then learn it.
oh, that's
Well, robotics is gone from
quiz,
Wednesday.
learn the quiz again.
no. Or Bill.
We should just do all the tests for the rest of the year on Monday.
I go with
Hey, Benny, you're
Yeah,
robotic
but I don't know how many people are showing up. So
I won't be on.
Joseph's gone, Quinn's gone, Patrick's gone.
No, you don't have a quarter.
all of us are here.
Last night. Yeah, I just like got up.
So I'm not sure how many are going to be here, but I'd like to get those logs done so I can send it off. We're getting close to the deadline. So I don't know who all showed up, but
Quality's not the best, but come on, let's be honest. We didn't get quality right.
You should have used like the 5-inch